Whenever you're trying to take the antiderivative of a trigonometric function, it's essential that you have the derivatives already memorized, right? We know that the sine differentiates to the cosine, etc. So that means that whenever we find one of these guys in an integral, then we know how to integrate it because it's just going to take us back to some form of the original function. Notice that I deliberately did not underline the negative signs here because that's just part of a constant. I don't really need to see the negative sign. I can see it there, or I can see it there, or I can see it there, I can see it there. Whether it's there or not, I don't really care. I just need to keep track of it, right? So, so when I take a look at something like this, I see secant squared of stuff. Well, secant squared is an answer that we get when we take the derivative of the tangent. So it's just the stuff we have to worry about. Is it okay that that stuff is not x, instead it's 8 theta? Well, sure. We're gonna use u substitution. We're just gonna let u equal 8 theta, which means that du over dx equals 8, or du over 8 equals dx. Now, I would imagine that some of you guys could take this antiderivative in your head without actually writing out these steps. I'm okay with that, but it's good practice to kind of make sure you understand this process of u substitution. And look at that. Just by default, I kind of got into this habit. There's no x's in this problem. Let's not do that. Let's be awake here. And d theta is actually what we want there. Anyway, so this is going to be the integral of secant squared of u, and d theta is going to be du over 8. So that 8 in the denominator can factor out. And we've got an antiderivative that we definitely know how to do because secant squared of u will integrate into tangent of u. So that 1/8 is still out front, but we've got tangent of u, and then our final answer would be 1/8 tangent of 8 theta plus c. So that's maybe we'll call it a baby integral. It's there's nothing much to it. It's pretty easy. That leading coefficient is just a constant, so we can just divide by that and we can kind of skip all that u substitution problem. Anytime we get into something a little bit more complicated, however, and then I would expect to see the process of finding a value of u and then actually figuring out what du is in terms of, in this case, dy, or dy in terms of du. So again, make sure that you're trying these on your own and then using the video to check. So I'll ask you, what do you think u should equal in this problem? Decide what it is, pause the video, and see what you get. All right, now that you've paused it and worked the problem, we know that the thing inside the parentheses is always a good thing to try to let u equal 2, so we'll let u equal y squared. That'll be kind of nice because then we'll have cosecant cotangent is one of those things that we have over here, right? We're expecting the answer to be the cosecant of y squared, or related to the cosecant of y squared in some way or another. So keep that derivative property in mind while we're doing this problem, because it's certainly going to come into play. So before we do that, let's make sure we can rewrite this integral in terms of u. So we know that du dy is equal to 2y, and then that means that du over 2y equals dy. So when we rewrite this, we'll get, well, that y out front, we're a little concerned about it until we realize what's going to happen to it. We got y squared is u, and we've got another y squared, so it's another u, and then dy is du over 2y. And that's where we see, aha, well, that makes us happy because the y in the denominator and the y in the numerator cancel each other out. The 2 doesn't cancel out, but I don't care. That's just going to get factored out. And we've got cosecant of u. We've got cotangent of u. And we've got du. And that's exactly what I need in order to do this integral. Don't forget the negative. Since we don't have a negative here, we have to have the negative in our answer, right? So we'll go ahead and have negative 1/2 cosecant of u plus c, or negative 1/2 cosecant of y squared plus c. And that would be the final answer for this one. All right, I've got a number of trig examples. I don't think I'll go through each and every single one of these because I need to leave some of them for you guys to try. So on this one, I'm going to go ahead and let you guys work it out on your own, this next one. But I will go ahead and tell you that for sure, the thing inside the parentheses is a great thing to let u equal. So, so go ahead and give that one a try on your own. And you can check your answer using derivatives, of course. This one might be a little bit harder to figure out what a good u value is, but let's keep in mind that we know that cosine to the fifth of x is the same thing as cosine of x times cosine of x times cosine of x times cosine of x times cosine of x, right? We just write it like this without the parentheses because it's easier to write it like this than like this. But when we write it like this, we are reminded, aha, there is something inside the parentheses. That is the argument that we can let u equal. And not only is that the argument, but it's also its derivative shows up in some form over here. So that's going to cancel out. And that's, again, that essential piece to this u substitution process, right? We've got f prime of g prime of x, and if f prime of g of x, and if g of x equals the cosine of x, then g prime of x, or negative sine of x, better show up in some form or another out here. If it wasn't for this sine of x out here, we'd be in a load of hurt at the moment. We don't have, well, there's a trig identity we could use, but we don't know that one yet. I take it back. It uses the Pythagorean identity. You better know the Pythagorean identity, but we're not going to do those right now. Anyway, du dx is equal to negative sine of x. So du over negative sine of x is equal to dx. So when we rewrite this integral, that sine of x, which we already know is about to cancel out, it can be written right there, and then we'll get u to the fifth, and then the dx is du over negative sine of x. Okay, so that's perfect because the sine of x and the sine of x are gone. That noble gas, argon. The negative gets pulled out front, and we have u to the fifth du. So we've got negative u to the sixth times 1/6 plus c, or negative 1/6. Well, that's cosine to the sixth of x. And I ran out of space here, so let me slide this over to the side. And write my final answer, boxing it in. All right, so just because there's a missing parentheses here doesn't mean we can't rewrite it using parentheses. So that's sometimes a helpful little trick. And let's see, we've got a few more trig examples. And I think I'm going to let you guys try those on your own as well. Think about the parentheses, where we can put parentheses. Also think about what a derivative of one thing is versus the other thing, right? So sines and cosines differentiate to go back and forth with negatives and positives, right? They flip around. But over here, tangent doesn't differentiate to secant, and secant doesn't differentiate to tangent. So make sure you're using those derivative rules wisely. So we might need to save a secant over here with the tangent because the derivative of secant is secant tangent. So play around with it and see what you can come up with. Jump down to taking a look at some definite integrals. Remember that definite integrals work the same way as indefinite integrals, all the ones we've just been doing, except we've got numbers over here. And so the process, that first fundamental theorem of calculus, is to take the antiderivative and then evaluate that antiderivative at these two values and subtract. So just be aware of what changing the variables does. So let's take a look at what happens here. If we take a look at this integral, at this point we should realize, oh yeah, this thing right here is in parentheses being raised to the 1/2 power. So this would be a great thing to let u equal to, right? Because that's what's inside the parentheses. So du dx equals 3x squared, or du over 3x squared equals dx. So I can rewrite this integral. Okay, I'm going to hold off on that 0 and that 2 for a moment. Be careful with those. Let me just get that x squared taken care of. We know it's going to go away because this u raised to the 1/2 is not the part, but the dx is going to equal du over 3x squared. Du over 3x squared. So the x squareds are in fact going to go away. So we can actually write this as 1/3 the integral of u to the 1/2 du. Now, I was very careful not to write the 0 and the 2 there. Why don't I just write a 0 and a 2? Well, because remember what this is. We're talking about letting x start at 0, x equals 0, and we're going to let x go until it equals 2. But if x equals 0, that's not the same thing as saying that u equals 0. If x equals 0, then u is going to equal 1. Let me actually write out where that 1 came from. So we've got two different things here. We've got if x equals 0, then u equals 0 cubed plus 1. And if x equals 2, then u equals 2 cubed plus 1. So we're not going to integrate this from 0 to 2. We're going to integrate this from 1 to 9. U is starting at 1 and going to 9. U starting at 1 is the same thing as x starting at 0. U going to 9 is the same thing as x going to 2. So this is a nice way to do it. It's not the only way to do it. Some people will say, well, I'll just do all of this and then go back to my x's and use my original values, and that's fine. To me, it seems like a little bit of extra work to do a little bit of extra substitution. And then for this one, we don't have to do any substitution back. But again, it's a matter of preference. But you definitely want to be familiar with this method because this is how it tends to show up in multiple choice problems. The 1/2 bumps up to 3/2, divide by 3/2, and we're not going to put a plus c here. We're going to put a 9 and a 1. We're going to evaluate that at 9 and 1. So 2/9 is a constant that's going to be the entire problem. We're going to evaluate 9 to the 3/2. We're going to evaluate 1 to the 3/2. We're going to subtract the 2 because that's the first fundamental theorem of calculus. Square root of 9 is 3. 3 cubed is 27. Square root of 1 is 1. 1 cubed is 1. So that's going to be 26 times 2, which is 52 over 9. And unless I made a mistake, that would be your final answer. So trying this next one using that same strategy, we're going to go ahead and say, well, general rule of thumb doesn't always work, but so far it has. We're going to let u equal the thing inside the parentheses. U equals the cosine of theta plus 1. So that means that du d theta equals negative sine of theta, which is great because we've got that sine of theta right there, so they'll cancel each other out, which is exactly what we have been seeing happen each time to this point. So when we rewrite this, let's see, pi over 2, the cosine of pi over 2 is 0. 0 plus 1 is 0. And then cosine, did I just say 0 plus 1 is 0? Gosh. 1. And then cosine of pi is negative 1. Negative 1 plus 1 is 0. I think I was thinking ahead to that. Sine of theta, I'll go ahead and write the sine of theta down there. It's going to go away, but oops, I'm not going to write cosine theta plus 1 though, because that's going to be u that we're squaring. And instead of d theta, we have du over negative sine of theta. All right. So the sines of theta cancel out, which we would expect. And we pull out that negative. The negative is out front, and we've got 1, and we've got 0. We've got u squared du. Well, this is interesting. We could forge ahead in its current form, but maybe with that negative out front, we can say, well, actually, we can just flip the order of these because of a property of integrals that we learned a few days ago, right? Flipping the order of these changes the sign. So we'll just go the more comfortable 0 to 1 of u squared du. And that's something we might be able to do in our head, but we'll go ahead and do it by hand. We've got 1/3 u cubed, evaluated at 1 and at 0, so we've got 1/3 times 1 cubed minus 0 cubed, which is just 1. 1/3 times 1 is 1/3. And that would be it.